Hi, I'm David Byte.
And I'm Darren Sutton.
We'd like to welcome you to this session on best practices for HPC storage. With that, we'll jump into the agenda. And really, it's pretty simple. We're going to talk about understanding HPC workload I/O and the storage options that you have in the HPC environment and specific thoughts around that storage and the best practices. So first, let's look at the HPC workload I/O patterns. Really, understanding this is one of the most important things you can do for an HPC environment. And that's because you may not need to spend as much money as you think to achieve what your HPC workload needs. And this gets into looking at things like, is the I/O steady in nature, or is it bursty? Does it do batch jobs? Does it require low latency, high throughput? Or is it really something that cares a lot more about a lot of small random I/Os? Each workload and code that you have in the HPC environment can have a completely different I/O pattern. So as we look at the topics today, we're going to try to get out some of this information and help you understand how to adjust for that. So let's look at understanding the current workload. The first thing is the majority of HPC workloads, and this comes from some industry data, things like climate and physics, perform large sequential writes. Now, this is not always the case, but when we're looking at the bulk of HPC clusters, that's what the industry sees. When we're looking at astronomy, genomics, again, these are down to small random I/Os, so a slightly different I/O pattern. And this translates in the end to a different need in the storage environment. Particle physics, large sequential read I/O. Again, slightly different here. And the one thing I will say is these are generalizations. If you're going to move down the path of trying to understand what storage is best and how to best deploy it, you really need to understand your I/O. And there are tools that you can use to do that. We're not going to cover those to any depth here today, but we're going to talk more about what the options are and where they fit in to these generalized I/O patterns.
I think one of the things to add in here as well is the workload that you have today may not be the same workload that comes along in the future. And this is something to be aware of, is that as scientists change what they're looking for, the workload patterns change and the things they're trying to do change as well. And this can cause a lot of challenges around trying to sort these sorts of workloads out and look at what the best solution is.
So when we look at where the codes are going, there's a lot of things that are happening. Like Darren said, we look at the codes today. Most of them are very old codes, things that were written in the 70s, 80s, early 90s. So looking down the road in the exascale, a lot of these codes are being revisited and being reworked, and this may very well change the I/O patterns there. So you definitely want to look at that. You want to talk to the vendors for the commercial codes. Are they changing the way the codes work? And there's now a lot of shifting interest as well. Traditionally we've used POSIX storage. Started with NFS and then PNFS. Distributed file systems, whatnot. Now they're looking at object storage. So with that, people are reconsidering how they do the storage I/O. So definitely, look to the commercial code vendors, talk to them. What are they doing from a storage perspective, and also talk to the communities for the public codes. Are they looking at integrating some of the new object storage and moving to that, and what kind of results are they seeing in those environments? So we'll let Darren talk about storage options.
So there are the challenge with storage that there's no one answer to every problem. And this really is the big problems that we start to get into. So what protocol are you going to use to access it? Is it going to be NFS? Is it going to be things like CEFFS and Lustre? Some of the commercial offerings like Spectrum Scale, things like Wicker.io, they all have different ways of solving the storage problem and giving you different characteristics of that storage. And that's why it's so important to understand what your workload is that you're trying to achieve, and then you can match the right storage solution at the back end. And some of these products are better at doing certain types of I/O than others, and some of them could be used in many different cases. And that really is the challenge there from a software perspective and what you're trying to do. The next bit then is around hardware, and some of this starts from data protection. Is your data so important that you need to do RAID for it? So you need to provide protection against disk failures, or is your data purely scratch data that actually takes virtually no time to recreate? So in that case, you don't care about protection of that. You want to have devices there that you can put on there, put your data on and write it as fast as possible, because if it's not RAID, it gives you potentially a much better throughput, because you're not having to calculate RAID checksums. Then you've got to look at the type of interfaces you're talking about. Is SATA good enough? SATA gives you a much cheaper price point, or do you need SAS with its better performance? And a lot of that comes down to how many devices you're putting behind the system as to whether you can have one-to-one connections. And then we get into things like SSDs versus NVMEs. There used to be a big price differential between SSDs and NVMEs. That sort of price differential now has pretty much eroded. So you're starting to see the same sort of prices for SSDs versus NVMEs. The challenges you get into that, though, is the number of NVMe devices that you can access at high speed could be limited by the number of PCIe lanes on your actual server. Whereas with SSDs, they could be SAS connected. You could have hundreds of SSDs connected behind a SAS controller. Then you get into problems about what you can drive through that. But at the end of the day, one of the things for all of this is your storage system is over on one side, your computer's on the other side, and they've got to get from one to the other. So what is the best options around that? Do you need the really low latency of InfiniBand and the advantages that gives, or is 100 gig Ethernet the place you need to be? And some of this may be down to what networks you have in place already, what you're looking to try and use. So these are the sorts of things to think about when you're doing that. And then you get into the complexity versus the performance, scalability, cost. So that's really where you start to get into some of the challenges here when you're trying to put a solution together. Does it matter that it's up and serving data in 3 days or 3 months? And that's down to some of the complexities of the software that you're trying to deploy. At the end of the day, the easiest way to deploy storage is you just plug disks straight into a server. But that doesn't share it. That doesn't give you some of the scale out and some of the performance that you may want out of the solution. And then there's questions about, okay, this particular product can give me a really, really fast environment, but am I actually going to use all of that performance? Do I need all of that performance? So we've been to things, some of the things like Formula One teams where they talk about, yes, well, we put in a really complex file system to manage all of this, but actually we're only using a fraction of the performance. And our bigger problems are the fact that trying to add extra capacity is our challenge. So for them, scalability is more of a challenge because it's not a simple task for them to add that capacity. How much data, how long are you going to keep it online? Some cases, the data may only need to be online for a very short period of time. They're going to process it, get the results, store the results away, and the original data gets thrown away. It's no longer needed. In other cases, they may want to keep it for a number of years because they may have to go back and reprocess that data. They may need to go back and look at and say, okay, so we did the test, we ran against that data a year ago. We now need to run the same tests against that data with updated information or updated algorithms to give us a better output or a different answer. So sometimes that's about, doing that. So autonomous drive is a classic example of that sort of thing. They've got a whole load of scenarios that they want to run through. They improve their algorithms. They want to run through all of those scenarios again to make sure that they get the same outcomes. At the end of the day, they're trying to stop cars crashing. So that becomes quite important to them. And what is the real TCO? Because sometimes if you put in a complex solution, that means you've got to bring in lots of people to water and feed it. And every time you want to do an upgrade, you've got to bring in another set of engineers who are going to be on site for a period of time to do this. This adds up to the overall TCO costs. And is that what you need, or is that what you're more after is something simpler? And we've got quite a few cases where people are saying, yes, I need a certain amount of very high performance storage. And some of the solutions we talked about before can actually build that and provide you with that. And then they are talking about a lot of the data, we just have to keep it. It doesn't need to be on high performance. We just may have to go back to it at some point in the future. So does that now get into a tiering, moving things onto the appropriate cost platforms as you need to do that?
So we're going to jump into a little bit about some specific technologies, and I'll start with Lustre. You know, Lustre is the granddaddy of HPC file systems. It's what you see in the large clusters in large quantities, right? I would venture a guess that we're talking somewhere in the neighborhood of 70 to 80% of all HPC systems use Lustre today. And really, while it's well known, Lustre can be very complex. It's not simple. You know, Lustre is really good at delivering low latencies and high throughput, but that comes with the cost of a lot of tuning. You know, and I point out a little bit of this here, but there's a ton of work that goes into getting Lustre just right. So much so that there have been people that have actually applied machine learning to Lustre configuration to make it perform well. That's a whole topic on its own, but an interesting use of machine learning. But the result is you know, you're really looking at something that while it's there's still a lot of knobs that you have to tune to get it to work right. And then in the end, there's also still some concerns by some elements in the industry around ZFS. You know, with Lustre, you can use LDISC-FS, which is a modification of EXT2, or you can use ZFS underlying it. ZFS is often the preferred today, but there are concerns still about patent encumbrance around ZFS with some attorneys. So we have to watch out for that. It's something to definitely be aware of if you're deploying ZFS in your environment. You know, you want to make sure that there are no legal ramifications. So, you know, talk to your attorney. So next, I'll let Darren talk about NFS.
Yeah, so NFS is obviously a granddaddy of the internet. You know, it's something that's been around for a long time. You know, for small clusters, this is probably a very good answer. You know, quick and easy to set up. Depending on the workloads you're doing, though, then lock-in can become a problem. And because of the way that lock-in's done, it doesn't scale that well because everything is running through potentially a single point when you're trying to connect to the storage. But, you know, with the size of disks that we have these days, you know, we're up to 18 terabyte disks now, then put in, you know, 100 disks in a single server, suddenly you're at a massive amount of storage on a single server. But it does have some challenges that, you know, lock-in is a single point, everything's going through that single point of connection. So those are the sorts of challenges you can get from an NFS perspective. Ceph is another option. And one of the challenges with Ceph is actually there's many different ways that you can provision a Ceph environment. So we can have POSIX file system, so CephFS. You know, the CephFS is built into the Linux kernel. And we've also got object interfaces. So S3 is the classic one that we see there. So we can scale it very well. We can scale horizontally. But the challenge with that is you have to think about how you're scaling it. You have to think about how we're going to grow this over time. The HDF group has done some work on a vol driver for Rados. So Rados is the native way that Ceph internally addresses the storage. So, you know, having a native driver for that means then you're getting the best performance out of Ceph. With CephFS, we've got entries on the IO 500 where typically we've been doing a lot of work ourselves at SUSE around this and doing, you know, testing of how fast can we push this, how can we drive that, but it's not typically well known in the HPC world yet. Obviously, CERN's a big one that sticks out there as using Ceph in a big way. But what we are seeing a lot of is Ceph being used as a tier behind very high performance file systems. So things like GPFS, Wicker, and Lustre, they've all got the ability to tier data down out of the high performance primary area onto a lower performance backend store. And typically most of those are done through an object interface. S3 is the way that that's normally done, and that gives you the ability to have that backend tier that just keeps growing and is not affecting or not changing your high performance frontier. So you keep your working set in the frontier with data that you need to work on currently. Once that's finished being worked on, it can be either automatically migrated, or you can schedule some jobs to migrate that data down into a lower cost tier and a low performance tier. Again, put in the right data on the right storage for the right price point is what's key here around doing this.
Yeah, so just a few more thoughts on Ceph and the HDF group's work. There's actually a paper by Lawrence Berkeley National Laboratory where they've done a comparison between Lustre and Ceph and DEUS. And what they really were looking at is how well do they actually scale? And what they found is Ceph actually scales better than Lustre given certain workloads. So it's an interesting paper, definitely one worth looking at. And I think what it really shows is the real emergence of object storage into the HPC world and bringing with it some benefits that come due to having something like an object storage backend. That makes a huge difference. So next, I want to talk about something that's really new, and that's DEUS. So DEUS is an upstream project. It's being worked on by Intel and a lot of the Department of Energy labs here in the US. And it's really a fresh start. It's designed for server class memory. So think NVDIMMs, Optane DIMMs, and NVMe technologies. This is not designed to work with spinning storage. And it is extremely fast, as you would expect of something designed for native NVDIMM type usage. That's really where we're driving latencies down far under, the millisecond boundary. You're talking, heading down into nanosecond type territory. And you're starting to see some emergence of this. It's made an appearance on the IO 500 list, but it's still very early in the life cycle of DEUS. So, I don't think it's ready for consumption for most people yet, but it's definitely something to be watching as we see, the price points of server class memory and NVMe technology drop and DEUS continue to mature. It becomes quite interesting. And on the back end, it also has data movers built into it. So like some of the things Darren mentioned previously, it has the ability to tier off of that very expensive, smaller tier of storage at the front that's very fast to a back-end technology like Lustre or Ceph or whatever.
So some of the best practices, you may want to tune a cluster to take advantage of certain things like C-states, but that may not be the thing you want to do with your storage. You've got to think about it. So what is your storage being used for? Does it make sense to set the CPUs in the servers to run at the highest power consumption all the time when it's for archive and backup? So the storage is spending most of its time not actually doing anything. So now it's consuming lots more power. So that becomes a cost conversation to have. Things like drive controllers. And this is one of the biggest things we tend to see is this sort of challenges around drive controllers and what happens with them. So we've certainly had cases where a 24 drive chassis that we have, and you have one drive controller that looks after 16 drives, another drive controller that looks after 8 drives. All of these drives happen to be SSDs. So you'd think that the drives that were behind the 16 drive controller and the drives behind the 8 drive controller would behave in the same way, but they didn't. The 16 drive controller was only giving about 1.2, 1.3 times what we were seeing from the 8 drive controller. When we switched it out from the 16 drive controller to 2 8 drive controllers, so in effect we had 3 controllers in the end, the overall throughput then was much better than the actual environment. again, things like multi-queue block I/O. So with modern SSDs and with cache and RAID controllers, then using multi-queue block I/O can give you a significant performance increase. With NVMe's, multi-queue block I/O is already turned on by default. But for other types of media, you have to do some changes around that. Things like looking at SAS versus SATA, and what types of drive you put in there, how much throughput are you looking to get to those, how are you connecting between your processors and the actual disks, and whether there's any switching in there that's happening from a SAS perspective. These are all things that you need to be aware of because they could slow you down. If you put 100 disks behind one SAS controller, you're not going to get the bandwidth out of all of those disks. But on the other hand, if you bond multiple SAS lanes together, as some of the vendors can do, go to 12 gig SAS, and suddenly that 100 disks behind a controller that's using multiple ports may actually be achievable and maybe something you want to look at doing.
So some more best practices as we look at the storage landscape for HPC, are very similar to generic HPC tuning. Things like looking at the I/O scheduler. Darren already mentioned the multi-queue block I/O. That's really important. But with SLUS 15, you're getting now multi-queue schedulers there as well. And it's important to look at how those behave for your environment and your workloads. So you may want to do some testing, iterative testing, as I talk about in the HPC tuning session, to go through and measure how those affect your particular environment. We'll often find things like NVMe's tend to work better with a no-op scheduler in place, right, when multi-queue is enabled, at least in the Ceph world. So there are definitely a lot of things to check there. When you look down this list, there's a few others that are kind of important. When you think about the storage system you're putting, is it NUMA aware? If so, you should turn off NUMA auto balancing. That's something that you could have those two battling each other potentially, and that's not something you want to have happen. Transparent huge pages. Is it recommended to be on or off? Again, important settings. And as we move down, obviously the security mitigations that are there for CPUs today, when we talk about the side channel attacks and whatnot, those are things that can have a performance impact. But before you disable them, you want to have a very serious discussion with the security group to make sure that, one, they're okay with it, and two, that you're not exposing yourself to potential compromise. And I do want to point out just one more thing on this slide, and that's really about thinking about the hardware layout. And that's everything from the CPU to the memory channels to the PCIe buses, right? So I have a preference. I don't like processor interconnects. If I can get away with one socket, I will. But keeping in mind with that, you also have a limited number of PCIe lanes for that. And you also have a certain number of memory channels. One thing on memory channels, I've seen this happen too many times where people will not fill out all the channels. They'll populate, the first channel or the first two channels on a socket. And what they lose is memory bandwidth. That may not be something that everybody thinks about. I kind of do. Maybe I'm weird that way. But you definitely want to not create artificial bottlenecks in your storage system. So let's move on into the wrap up and talk about the conclusions we've drawn. So the first thing I'll say, what you did yesterday for storage is probably not what you're going to do tomorrow. This is a space that's changing. We're starting to see a lot of rapid change. You see that with Ceph becoming more and more important, object storage in general. You see that with DEUS, with the new memory, with the new storage class memory technologies. So there's a lot of things. You also need to know where your codes are going. What are they doing from a storage perspective? Are they implementing new hooks to do object storage? Are they implementing server class memory hooks? What's going on there? Darren?
So, yeah, and tuning the environment appropriately. And that's a key point here, because you could make a set of tuning parameters that work with one specific workload, but they're so specific to that workload that it degrades other workloads that may be running on the same storage. So you've got to understand what you're actually trying to do from that perspective. And looking at, available options, again, does it make sense to split your storage up into different types of storage for different use cases, or does it make sense to spread everything across every node, because then you get the performance and bandwidth for every node that's out there. And certainly, looking at, what is the long-term view of this? If you're going to grow from 100 petabytes today to 500 petabytes in 5 years' time, that's probably one type, that will probably guide you down looking at one type of storage solution as opposed to another type, because you need something that's easy to add and easy to grow, which is not always the case with all storage solutions. And the last one there is, don't lock yourself into a technical nightmare. I've worked with banks where they have people employed just to replace the arrays as they go out of date because they have so many arrays there. The actual effort involved in doing that is a full-time job for someone just migrating data from one array to another. And then you get into the situations where ultimately the amount of data that's appearing now, this may be something that you can never actually keep up with. And there was a telco I was working with who had got to the situation where he recognized that actually the amount of new data they were going to be ingesting was faster than the rate at which they could get old hardware out of the environment. And this is things that you have to think about. What happens when something gets to being 3 years old, 5 years old, whatever your hardware cycle is, and how are you going to get out of that? And how are you going to move 100 petabytes from storage cluster A to storage cluster B? This is not a small task that can be done in a few hours. And that's really the things that you have to think about, and how you don't let that be a problem for yourselves.
Yeah, so talking about the technical nightmare a little more as well, one of the challenges we have in the storage space is there's always new innovation coming in. And the worst thing you could do would be to jump on something that has just come out and deploy that as your primary HPC storage, and then get so much data on it and get your processes so intertwined that it's nearly impossible to extricate yourself when it falls by the wayside. We've certainly seen that happen across the time I've been in the business and Darren's been in the business. That storage products come and go, storage technologies come and go. Just be aware that what you implement today, if it's really bleeding edge, it may not last 2 to 3 years. It may quickly, someone find a problem with it or find a better way of doing it, and it gets jettisoned. So, that's yet another technical nightmare to be aware of and be wary of. So with that, we'd like to thank you for watching this session, and hope that you have found it useful, and that you would continue to visit and see other SUSECON sessions. Thank you.
Thank you.